Okay, welcome everybody to this new episode of the podcast Coffee Breakdown. I am Luca, and actually the aim of this podcast is to shine some lights into different field of research, also to give space to students, PhD students or master to show their research, and also to more senior scientists to express their opinion about our field. And today we have with us Rouven Lamprecht, who's a PhD student at the University of Kiel in Germany. First of all, thank you very much, Rouven, for being here and sharing your work with us. And yeah.
Yeah, thank you for the invitation, of course. Nice to talk about this topic. And yeah, my name is Rouven, as you said, and I'm a PhD student in Kiel, and I'm working on memristive devices or searching for new materials for this field, I would say, and in the general border of neuromorphic computing. So I hope I can get some information.
Okay. Yeah, exactly.
Yeah.
Actually, okay, you already introduced some terminology that is very interesting that I think not all of our public is familiar with. So these memristive devices, but first of all, I would start with this neuromorphic computing that you were mentioning. So what do you mean by neuromorphic? Because we are used to classical standard computing, right? Based on standard CMOS technology. So yeah.
So yeah, the memristor is a part of neuromorphic computing. So one little part. So it's a good idea to talk about neuromorphic computing first. Since we all know the normal computer, I would say we all have in our smartphones, or we are talking over a normal computer now. So there's a rise in interest in machine learning and new data-driven computing, I would say, and therefore we have we tend to we have a new topic of this data-centric computing, which is just a bit problematic for the normal logic-driven or control-centric computing from Neumann computing. So the normal computer we are using is a von Neumann architecture, and therefore we get to an end of this this type of computing, because it's the new computing is kind of highly power consuming, and we need a lot of data has to be transformed from during the computing unit, the CPU, and the memory, and therefore researchers are searching for a solution to have maybe two topics like this in-memory computing. So we have there's a bottleneck between this data transfer between the memory and the computing part.
Yeah, and this is one of the actually main structure of this architecture, right? The division between CPU and the memory, basically. Exactly. And so the passing information is becoming really bottleneck if you're doing like AI or this type of application. That's true.
Yeah, exactly. So I would say they try to optimize this by having this in-memory computation. But another approach is to use this neuromorphic computing aspect. Like when we look at our brain, it's just that we have this highly complex system which can compute a lot of stuff. So when we look at a picture, I can clearly see, or if I look at you, I can clearly see, oh, this is Luca in like a few milliseconds.
Yeah, that's
true. If I would use a computer just to make the same computation and see if this is Luca I'm talking to, he has to compare the image with a lot of data, and it's highly power consuming. So in neuromorphic computing, we try to mimic the brain, or this is why it's also called bio-inspired computing. And it's beneficial because of course we only use a few hundred watts in our brain.
Yeah, this is interesting. And I think, this is one of the main points. This is also, to my understanding, one of the limitation, of this Moore's law of this scaling, that you can make devices smaller and smaller. Exactly. So you can, of course, perform more computation. Nevertheless, when you increase also clock rate, you increase power consumption kind of linearly. So,
Yeah,
you
exactly.
know, so this becomes kind of problematic in the modern architecture. Whereas we want to have, from what I understood also from what you were saying, you know, we want to have something that is less power consuming. So yeah, that is very interesting. So, okay, so then actually, so this is something that is in an advanced phase or is being researched now. So what is your feeling about the topic? Are there also companies or private sector investing in it, or it's just starting? Do you know about that? Or?
I would say it's in the early stages of research,
Okay, okay.
because all this we are still trying to figure out how the human brain works. So there are a lot of research groups who are just searching to understand the synapse, the neural networks and stuff like that. So if we don't understand the neural network, we can't mimic it by electric components. So I would say it's still in the early stages, but still there's a lot of investment in this topic from the big companies, because they know that the current architecture isn't working out for the future, so they also have to invest in different areas, of course. But I think we need some more years for this. And I think a common mistake is that this neuromorphic computing is not a supplement to the structure, the computing we are using right now, but more like a new aspect or a new add-on. Or I don't know how to say this, but so the control-centric computing is still used, but we can make it better by
Complement,
applying
exactly.
some.
Okay,
Yeah, exactly.
I see. So future
just a new
devices
aspect.
will have different components, some of that based on standard CMOS technology, and some of that with this memristive that now we're talking about, I suppose.
Yeah, exactly.
Okay, very interesting. Another thing that is always puzzling to me is always, you know, because we say always, okay, we want to mimic the brain, right? But of course, the clock rate, I mean, the number of computation we can do per second is very different than what the computer can do, right? So it's not that we really have a brain made of silica or something like that. It's totally different. So there are still differences, I think, right?
Yeah, so we still have to train the network, and we still have to make the network learn over a few, not in milliseconds. So we can't give it a task and some seconds later we have the result like the normal computer, but we can train the system for a task we know, for example, image recognition or something, and then we get out the after we trained it, we get out a result in still a small time sample. But of course, it's not that easy to learn. So if we compare it again to the human brain needs years to learn things like walking, like image recognition
Exactly.
and
So
stuff.
it's not really one-to-one comparison, because we
No.
still have to understand biological
Yeah.
system, how they work. That is true. You're right. I think so. You're
But
right.
when you can compare it more to the software-based machine learning, for example, where we also have to train the system, and afterwards we can use the system for image recognition, maybe. And so if we train the network right over, I don't know how long it takes, but if we train it right, then maybe we can use systems like this for example, autonomous driving or something, where
That's true.
they clearly can see on the street like a human brain. So
okay. I would like still to focus on this hardware part, because I think most of people are familiar with the software part, you know, kind of using machine learning. We know a lot of applications, machine learning. But the hardware part is something that a bit less people talk about. This is my feeling, at least. So can you describe how do you, you know, which type before you were mentioning about this memristive device. So what are those type of device, and how can you make it? What is their structure, basically? Is it very different than transistors, for example?
Yeah, it's more simple, but if we go to the start again, so the human brain consists of many neurons with connected by axons, and then you have the synapse, which is the part where by strengthening and weakening we get this different connections between the neurons, and these the hardware part is, I would say, first the software, machine learning and artificial intelligence and stuff like that is just that we learned that we can do these neural networks with hidden layers, and the connection between these and the weights of the different synapses kind of, and that we learned about this during the software part, but it's still hardly power consuming, so we need a new way to use this. So it's kind of the same, but that we have this synapses which are have the weighting by changing the resistance, and then there's the memristor which comes in, because this memristive device, or the memristor, tries to mimic the synapse. So we have just a simple structure, so it's more like just two electrodes, or it's just a one material in between of metal, for example, and then this material changes its morphology in different kinds of ways. So there are different kinds of memristive devices, and therefore the resistance changes. So and so the memristive, which is called memristor because of it has a memory, and this is a resistor. It can memorize the what happens in before. So if we apply a few voltage pulses to it, then it changes the resistance according to these voltage pulses, and therefore it has learned which resistance it should get, and then we can use it as a weighting synapse, for example.
Okay, that is very clear, I think. Okay.
So in comparison for the transistor, for example, I think it's still a two-terminal device. So we just use it as like a normal resistor, and we have just maybe one layer of different materials, or two layers, and that's it. So it can be scaled down to in the nanometer range, I would say. And
okay. Yeah, exactly. So that's interesting. So there are two aspects. First of all, you mentioned some materials. So which material typically is used to produce this layer, or this insulator layer typically?
There are a few different. There's dielectric. In general, we use dielectrics for this, and or insulating materials, which get conductive by applying these voltage pulses. And for example, of course, everyone tries to use CMOS compatible materials because they can use these in the same fabrication as
exactly. That's
the
also
normal
an
computers.
advantage.
Exactly. So, for example, the first memristor, which was with titanium dioxide, for example. Then, of course, there's silicon dioxide or copper oxide. These are like nickel oxide, zinc, zirconium oxide,
so
hafnium
these metal
dioxide, materials
oxides,
like this. So
okay.
they are mostly with oxides. So at least in this neuromorphic computing, you can use different materials as well, but I would say the most promising materials so far are these oxide-based materials.
Okay, that's interesting. I was reading, but I'm not expert of it. I don't know if you so also materials that exhibit this type of resistive switching properties by changing magnetization. Do you know something about it, or I don't know? I think this is totally different, right?
Yes. So these, by changing the magnetization or stuff like that, this is more for the basic memory, I would say, or the where we can store these binary input. But for normal of computing, for example, we like to have more an analog switching behavior. So we changed the resistance for multiple states, and therefore we can have like an area between a few ohms and hundreds of ohms, and this is not a binary like we are on an on state and off state, but more of in between of this.
Okay, okay. Okay, and regarding the fabrication, you mentioned basically this is very similar or actually the same to what has been performed. So how do you fabricate this device in your lab?
So in our lab, we are using the magnetron sputter deposition as well as evaporation. But in general, I would say there's also atomic layer deposition and chemical vapor deposition techniques. But I think since this is in the early stages of this research, and the stoichiometry of the devices is very important. It's, for us at least, very beneficial to use this sputter disposition or evaporation, because we can easily change the composition of the switching layer and get faster results for different stoichiometries and see what works and what not.
Okay, okay, okay. So basically, then you are trying also to investigate different materials and so on, and try to fabricate different type of devices then will be used for this neuromorphic computing. This is the core of your research, right? If I understand correctly.
Yeah, exactly. Yeah.
Okay,
So
okay.
I would say that we try to find new materials, because when you compare us to the industry, and we make a research on a material which is well known already, and we get in, we try to compare us to like Samsung or something like that. I would say they would be faster in every aspect.
Yeah, exactly,
But
exactly.
that's why we concentrate on these new materials and see what else is possible, since the promising materials they are using so far, yeah, they still have some drawbacks, and maybe we can find something even better, and this is, I would say, the interesting part about my research. So
exactly. So what are you excited about your research? So is there something that is very fascinating for you? Or also that your colleagues around you are investigating, for example? So what do you like about this neuromorphic computing field?
I like, especially I like that this is some really new stuff, and you can it's like when you make a measurement, and we are doing these IV curves. So we measure the current flowing through the device in comparison to the voltage we apply to it, and when you see the device and you find a new structure or a new stoichiometry and you test it out, and it nearly feels like the device is alive. So
Okay.
yeah, it's kind of funny maybe, but you really see like that there's something happening in between these electrodes, and the stoichiometry changes, and you have to find the perfect composition that this device stays alive, I would say. And that makes quite interesting for me, because when you then connect these devices to a network, then maybe the whole network gets even more alive.
Okay, that's very interesting. I have one final question that is puzzling me also. I think for this type of devices, what is important is also the durability, right? Because if you compare with other silica devices, then what's the current status, at least of your device, the device that you make? What do you think, for example, if temperature changes or if time also,
Yeah, of course. This is the big drawback. So we achieved like if that it's from so in general, for memristive devices, there's this drawback of cycle to cycle variability. So if we want to use it for in-memory computing, and we use a memristive device and it changes the resistance from every pulse, then it's not suitable for our for a big company, for example. So this is a drawback, but so far I think at least for me, we achieve like retention times so that it holds the state over multiple days sometimes.
Okay.
But of course, you need different scales in comparison to this in-memory computing, or at least or the phenomenon computing, because there you need like 10 years of retention time, or the storage of the information. And in our case, for neuromorphic computing, sometimes it's even okay, I would say, if it loses its state after 15 minutes. So some research groups are interested in this as well, because they need different approaches to this neuromorphic computing. But so far, we achieve like a few days, and cycles to cycle stability is kind of okay. But yeah, of course, this is, since the new materials, it's not that.
So this is one of your, let's say, main challenges of your project, of your experimental activity, I think, right? So to have devices that perform well, also that have some sort of stability.
You always have to compare with the industry standard, or at least next to it. So yeah, of course, this is always a challenge to get at least next to these parameters. So yeah.
Okay. Yeah, is there something else you want to promote or you want to say about your research, or if not, I would like to thank you.
Yeah, no, I'm totally fine. Thank you.
Okay, and thank you very much, Rouven. I think this is one of the first episodes actually that we make about neuromorphic computing. So hopefully in the future we'll have also more students and other people participating in this podcast. So you are a kind of a pioneer, so you should be proud of it. So and see you soon, actually, and see you around.
Yeah, thank you very much. Bye bye.